Question 4.2. Consider the system that can be described by the differential equation by this input-output relationship, which is in the form of differential equation. So let's focus on part A. And here we have to find the transfer function, and this is the way we calculate the transfer. We compute the transfer function. Okay, so just assume for a signal xt, if we have this signal xt, it's a Laplace transform. We show that by capital S x of s. Okay, so if I take the derivative, first order derivative of this signal, then we would have d of xt divided by d of t, and the Laplace transform of this signal, this derivative, is s times x of s, assuming that the zero initial conditions are actually available. So that means I can the Laplace transform of this input-output relationship is in this form: s times y of s for the first item, plus 4 times y of s, because Laplace transform of yt is capital Y of s, and this equals s times Laplace transform of dxt over dt is s times x of s. Okay, so now I should isolate ys and xs, so we can write it like ys times s plus 4. This equals s times x of s. Okay, and that means we can write ys over x of s equal to s over s plus 4. Okay, that's the answer for part A. This is the transfer function, s over s plus 4. Let me write it here. hs equals s over s plus 4. Okay, part B. How can you compute the system's steady-state output? Okay, system steady-state output. Steady state, that means when t goes infinity. Okay, given the transfer function hs, which we have it here, and the input, just assume input is x of t. Let me write this in different color. We assume x of t equals sine of 2t times u of t. Okay, well, since we say okay, this is the input to the system, so we have a system input. We want to find the system output at a steady state. Okay, so let me see if we can further simplify this or not. Can we simplify this xt or not? Well, we know ut equals either 1 or 0. It is 1 if t is larger than or equal 0, and it is 0 if t is smaller than 0. Okay, since we're considering the signal at the steady state when t goes infinity, then that means ut equals 1 and never equals 0. So let me then replace ut by 1. If I replace that, then we would have xt equals sine of 2 times t. Okay, so this is xt. And what should we do? Well, we know in LTI systems, because we're talking about LTI system, okay, all this chapter. In LTI system, if you have a system here and the input is a, say, sine of omega t, well, we have a property, we call it sine in sine out. That means if input is a sine wave, a sine signal, then the output would be also a sinusoid signal with the same frequency. But there might be a change in the phase of the signal and the amplitude of the signal. So this is the output. So bear that in mind. In a LTI system, we have this sine in, sine out property. And that means if the input is a sine wave, is a sine signal, okay, the output would be also a sine signal. It's the same frequency. Only its amplitude and its phase might be changed. And if it's cosine, we would have the same. The output would be a cosine with the same frequency and a possible change in shift and in phase and in amplitude. But so that means we should, if we know this is the input to the signal, the output is something in this format. If the input is sine of 2t, then the output is something in the format of a times sine of 2t plus phi. So the only thing we need to do is to find this a and this phase, this amplitude and phase. Okay, we can do that using a transfer function. Let me write it here. So if we have transfer function, then we can say a is magnitude of the we can say a is magnitude of frequency response, okay, and phi is actually the phase of frequency response. But we have the transfer function, not the frequency response. But that's fine because frequency response, so let me write it here, frequency response is actually transfer function given that s equals j omega, or the real part of s is 0. Okay, so that means if I replace s by j omega in this function, we can find the frequency response, and that's the relationship between frequency response and transfer function. So that means a equals magnitude of h omega, or magnitude of the transfer function, given that s equals j omega. And this also equals the phase of, this equals the phase of hs, given that s equals j omega. So let's calculate this. So I need to find the amplitude, I need to find the phase shift. Okay, if I want to write that here, well, h of s, given that s equals j omega, is j omega over j omega plus 4. So if you want to calculate the magnitude of this, let me write it here, the magnitude of this, then that's equal to the magnitude of the nominator. Okay, before that I should replace omega by 2, because we know already what is the omega. Okay, we know the omega is 2, so this equals j2 divided by j2 plus 4. So if I want to find the magnitude of the transfer function, then this equals the magnitude of the numerator divided by the magnitude of the denominator. So I may need to replace everything we have here. Make some space. You can write it here. Well, the magnitude A equals the magnitude of the denominator, which is square root of 0 squared plus 2 squared, okay, divided by the magnitude of the denominator, and that's 4 squared plus 2 squared. So you may think, how did I get this 0 here? Well, I can write this as 0 plus j2, okay, like a rectangular form of, this is 4 plus j2, rectangular form of the complex number, and this equals 2 divided by square root of 20. And in the same way I can find the phase. The phase equals the phase of the numerator minus the phase of the denominator, okay? And the phase of the denominator is, so let me see if we can make some space here. If I start writing from here, we can probably. Okay, so the phase of the denominator is phase of 0 plus j2 minus the phase of the denominator, which is 4 plus j2, and this equals arctangent of, or can write it in this format, arctangent of 2 divided by 0 minus arctangent of 2 divided by 4. Okay, so that means phase equals, for this one we have 90 degree, and let me pause the video, then I can either calculate this one and the angle for this one to see. I'm using calculator, so let me pause the video for a second. Well, I calculated a magnitude here using calculator. Well, it equals almost equals 0.0447, and the angle here, the arctangent of 2 or 4, is almost 26.5 degree. So if I do the calculations, you get 63.5. So that means I can write the output of the signal yt, which is equal to a times sine of 2t plus phi. This equals 0.447 times sine of 2 times t plus 63.5 degree. This is the output of this system for this input and for this transfer function. So bear that in mind, that we didn't have the frequency response, but frequency response is actually the relationship between frequency response and transfer function is that frequency response equals transfer function when the Laplace transform variable s equals j omega, okay, or its real value sigma is 0.